Hi everyone. Today we'll be finishing our chapter 19, which has been on spontaneity of chemical reactions and processes. And today we're going to start to talk about Gibbs free energy, but we're going to apply it to a situation that's called non-standard. So everything we've done so far has been standard delta G, and today we're going to learn what non-standard means. So after today's video, you should be able to understand the meaning of standard Gibbs free energies. You should be able to use the standard Gibbs free energies, and we know they're standard because they have this little knot. We should be able to use those to calculate delta G, that's without the knot, under non-standard conditions, and we'll define what non-standard conditions are. And finally, and this is a big one, we're going to be able to relate thermodynamics and spontaneity to equilibrium, as in Q and K. So we've got a lot to do. Let's get started. First of all, let's talk about what we mean by standard conditions. And notice here, as I said just before, the little knot up there means that we are talking about standard. In the past, for like delta H's or delta S's, that has meant 25 degrees Celsius and 1 atm pressure. The problem with Gibbs free energy is that we could have a lot of different types of systems. They could be liquids, they could be solids, they could be solutions. And so we have to give a few extra specifics on what it means for something to be standard. Because whenever we look up one of these values in the back of the book or on the internet, it's already going to be for these certain criteria. It's going to have the little knot there. So remember, we can use these values, the delta G knots, the standard values, to calculate the overall delta G naught of any reaction. And we do this just the same way as we have with delta H's in the past or delta S's. It's going to be the delta G overall for the reaction. We add up the delta G's of all of the products. Don't forget to multiply each product by its coefficient in the balanced chemical equation. And then we're going to subtract out the sum of all the delta G's of the reactants. Also, don't forget to multiply each one by its coefficient in the BCE. So hopefully that equation looks familiar to you from earlier in the chapter. The problem is, what if we're not under these standard conditions? And I'm going to show you a formula in just a bit that will allow you to switch from this delta G naught to a delta G under any conditions you desire. Let's talk about what standard means real quick. If we have a solid or liquid, it has to be pure. If it's a gas, it must be at 1 atm of pressure. And for a solution, it needs to be 1 molar in concentration. Sounds great, except for the fact that gases are almost never exactly 1 atm, or solutions are almost exactly never 1 molar. And so we're going to have to account for this. By the way, for an element, we define the standard Gibbs free energy as 0, as long as it's in its typical state of matter. As in hydrogen, if we have pure hydrogen, as long as we're talking about a gas, it has a standard delta G naught of 0. Let's move on and figure out how we can switch these to delta G's under non-standard conditions. So what if we're not at standard conditions? In that case, we're going to define the delta G, that should not have a knot there. We're going to define delta G without the knot to be this. Delta G under non-standard conditions equals delta G naught, that's standard conditions, plus RT ln Q. And you might be wondering what Q is doing there. Yes, that's the Q from equilibrium. It's the thing that we compare with K to see whether we're at equilibrium or going to shift forward or reverse. So let's define these things. Obviously, R is that ideal gas constant, and we're going to be using the one with joules because Gibbs free energy is an energy, so we need to make sure that we have joules in there. T is your temperature. Obviously, that needs to be in Kelvin. And the ln Q, remember that Q is that reaction quotient. So we calculate Q in exactly the same way we calculate K, except Q applies to any situation, whereas K only applies to equilibrium. Now, I want you to pause for a moment and think about what happens if all of your solutions are 1 molar. Can you make a prediction to yourself? What happens if all of your solution concentrations are 1 molar? Well, let's take a look. When all of the solution concentrations are 1 molar, remember Q is just going to be some concentrations to some coefficients over some concentrations, who knows. But if everything is 1, no matter what our equilibrium expression looks like, Q is going to be equal to 1, because 1 times 1 times 1 divided by 1, 1, you get it, it's 1. What's the ln of 1? 0. So if the ln of Q equals 0, then this whole term goes away, which means that this one goes away because they're being multiplied. So when all of your concentrations are 1, your delta G equals delta G naught. Why does this make sense? Because the definition of standard conditions says that everything is 1 molar. So if everything's 1 molar, we are at standard conditions, and our delta G is just equal to delta G naught. Hopefully that makes sense. So let's try a problem. We're going to relate our value for delta G to a phase change at equilibrium. So first of all, let's write the chemical equation that defines the normal boiling point of liquid carbon tetrachloride, CCl4. This was used as a dry cleaning fluid for a long time. Probably some places still use it. It is carcinogenic, so it's not very good for you. I would recommend going ahead to pause the video and write a quick little equation to represent the boiling of carbon tet. Okay, so it seems pretty straightforward. We've got CCl4 as a liquid, and it's going to CCl4 as a gas. One thing that you might have forgotten is that we're talking about the boiling point. And hopefully you remember that phase changes are always equilibrium situations. So I actually need to use my reversible arrow here, because as long as I keep this at the boiling temperature, I'm going to have both the liquid and the gas in equilibrium with each other. One other minor detail, what does normal mean? And of course, normal is referring to the pressure. So because they said the normal boiling point, we must be talking about a pressure of 1 atm. All right, let's move on. What is the value of delta G naught for this equilibrium in part A? So go ahead and take a moment and see if you can think of this to yourself. Well, hopefully you remember from earlier in the chapter that when delta G is less than 0, a process is spontaneous. When it's greater than 0, it is non-spontaneous. But when delta G equals 0, it is at equilibrium. And since we're talking about equilibrium, it's really just that simple. Anytime we're talking about equilibrium, delta G must equal 0. So the delta G for this process is, if you're skeptical, we can look at that equation that we just learned. Delta G equals delta G naught plus RT ln Q. And let's ask ourselves, what's Q? Do we have a gas? Yes, we do. So Q would be equal to the partial pressure of CCl4, and we know that that is equal to 1 atm. And we all know that we leave liquids and solids out of the equilibrium expression, but if we did, it would be down here. And all we care about for the liquid is that it's pure. And so for a pure equilibrium situation of this pure carbon tetrachloride, since Q is equal to 1, then the ln of Q is equal to 0. That process drops out, and delta G is the same as delta G naught. And since it's at equilibrium, it is 0. Let's move on to part C. Part C is asking us to use data from the appendix, and we're going to use that equation, 19.12, to estimate the normal boiling point of CCl4. And just in case you forgot what equation 19.12 is, it's delta G equals delta H minus T delta S. And in this case, this T is going to be our boiling temperature, so I'll put a little b there. Now, this is interesting. We don't know what the boiling point is, but do we know some other values? We know that delta G is equal to 0 because we're at equilibrium. We can look up delta H in the back of the book. We'll have to calculate it, I believe, but same for delta S, but we can find both of those in the back of the book, so you may want to take a look at the Appendix C. So looking at Appendix C, first of all, I'm going to remember the delta H naught for this reaction is going to be equal to the sum of the delta H's of the products minus the sum of the delta H's for the reactants. And I remember that I just have liquid carbon tetrachloride turning into gaseous carbon tetrachloride. And so all I'm going to do is find my delta H of formation for my product, carbon tetrachloride gas, and that is negative 106.7 kilojoules per mole. And in this case, since I have 1 mole of each thing on both sides, I don't need to worry about the multiplying by the coefficient. And then I'm going to go minus the reactants, and I see for the liquid carbon tetrachloride it's negative 139.3 kilojoules per mole. So that gives me a positive value for delta H overall for this process, 32.6 kilojoules. Why does it make sense that this delta H is positive? Yeah, so we know that evaporation or boiling is endothermic. So to go from here to there, we have to add energy. And we know that any time that delta H is a positive number, we consider that endothermic. We can do the exact same thing for delta S by summing the products entropies, subtracting out the reactants. So we've got 309.4 joules per mole Kelvin. One nice thing about entropy is we never have those negative numbers to deal with. Why not? Well, 0 is the lowest entropy can go. And that's probably not even possible because you would need a perfect crystalline structure and it would kind of need to be at absolute 0. So enthalpies are always positive numbers. And when we do that, we get positive 95.0 joules per Kelvin. Now, this was assuming 1 mole and 1 mole. So if you notice, I've removed the mole from the unit. So now we have our delta H and we have our delta S. How can we find T? I'm going to bring this equation back down. But this time we know that delta H must equal the boiling temperature times delta S. So the boiling temperature, if we were to estimate it, should be the ratio between the delta H of this process and the delta S of this process. I'm being a little bit sloppy here. These should all be knots because those are the only ones we can look up, are the standard values in the back of the book. And I'm just going to take my 32.6 kilojoules and divide that by my entropy, which is 95.0 joules per Kelvin. And this is why we use units, because I'm going to catch my mistake here. I need to get this joules into joules or vice versa. So I know that there's 1,000 joules for every kilojoule. And so now I can cancel out my joules, and the kilojoules also cancel. And I'm left with 1 over Kelvin, which is Kelvin. So that gives me 343 Kelvin for correct sig figs, which is around 70 degrees Celsius. So to bring that back to the dry cleaning, that's not a super high temperature you have to get to for the quote-unquote liquid carbon tetrachloride to turn into a gas. And so that liquid and the gas permeates through the clothes, especially clothes that water can't come into contact with, like silk, and that is how it removes stains and things. Also, one cool thing about it, carbon tetrachloride is nonpolar, and so it is good at removing grease and oils and fats because of its nonpolar character, whereas water is not so good at that. Okay, let's give one a try. This is actually easier than it looks, so don't get intimidated by it. If the normal boiling point of a liquid is 67 degrees Celsius and the standard molar entropy change for that is positive 100 joules per Kelvin, estimate the standard molar enthalpy change for the boiling process. So take a moment, jot down your work on your paper, and consider this answer. And the correct answer for this was C, positive 34,000 joules. If this one didn't go so well for you, or you don't feel great about the last exercise we just did, you should take a look at sample exercise 19.10 in your textbook. Now let's talk about free energy and equilibrium. So we already know that at equilibrium, Q is equal to K. And we agree that when delta G equals 0, there's no more free energy to go in either direction, and so we must be at equilibrium. So let's plug some things in. So the equation, which I forgot to put here that we're starting out, is delta G equals delta G naught plus RT ln Q. And when we plug in 0 for delta G, we find that it becomes delta G plus RT ln K equals 0. Well, let's solve for the delta G, and we're going to find that delta G equals negative RT ln K. So to rephrase this, when we started with the equation which we learned at the very beginning of this video, which applies to any situation, but when we plug in the special situation where we're at equilibrium, we end up with getting this equation down here. Delta G naught equals negative RT ln K. Why is this important? Take a moment to think about that. This is so important because we have this relationship between thermodynamics, which tells us whether something happens or not, and equilibrium, entropy, and enthalpy. All of these things are now tied together. So basically, if we know the delta G for a reaction, we can find its equilibrium constant, and vice versa. Just a note about this K, it can be a Kc, it can be a Kp, just a couple of reminders. So for gases, we're always going to use ATMs, which you already remembered from our unit on equilibrium. For solutions, we're going to use molarities, and solids, liquids, and other pure substances do not appear in that equilibrium expression. Another way of putting this is if I solve for K, K is e to the negative delta G naught over RT. So choose one of these equations that lets you calculate what you need. They are the same equation. One quick little question to ponder. Can K ever equal 0? Can K ever equal 0? Take a moment, ponder that. We'll see if you're right. So if I get out my calculator and I type in ln of 0, I get error domain. And that's because the natural log function is undefined there. So K cannot equal 0. Remember, K is the ratio of products over reactants at equilibrium. So K could be very, 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 very small. If we have very, very few products and mostly reactants, K is going to be tiny. But remember, we only use K for equilibrium situations. So if we have 0 products at equilibrium, it doesn't even make sense to call it equilibrium. Can Q ever equal 0? And the answer is, of course. But that would be at the very, very instant that a reversible reaction began with only reactants and no products. But we could never have a K equal to 0 because K is defined as being the ratio of products and reactants at equilibrium. Let's try a problem. This time let's try calculating an equilibrium constant when we know the delta G. So the standard delta G for the Haber process, remember that is for synthesizing what very important molecule? Ammonia from nitrogen and hydrogen. So the standard free energy change is negative 33,000 joules per mole, which is pretty big. Wow, why do we have this whole complicated process to take the nitrogen in the air and mix it with hydrogen, which is pretty easy to get, to make ammonia, if I can see that it is so darn spontaneous? Isn't this happening as we speak? And the answer is yes. But remember, this branch of chemistry is thermo. It tells us about spontaneity, non-spontaneous. It is an entirely different branch from kinetics. So the problem is it could happen at room temperature, but it's extremely, extremely slow. So when they do the Haber process, they increase the temperature to 300 to 600 degrees Celsius, which increases the rate of the reaction and helps to shift it to the right. But anyway, let's try this problem. And can you think of the equation we're going to need to use? So we're going to use this value to calculate the equilibrium constant for the process at 25 degrees Celsius. This is important. The delta G is tied to the temperature. That's a standard delta G. And remember, K is also tied to temperature. So the temperatures are important here. So which equation are we going to use? We know that K equals E to the negative delta G naught over RT. So just be really careful with your signs here. We've got negative 33,300 joules per mole. And we're going to divide this by quantity. I'm going to be careful here too. 8.314 joules per mole Kelvin. And that is multiplied by 298 Kelvin. So let's see if we can clean up some of our units. Kelvins go away. And I've got joules per mole, and it's being divided by joules per mole. So they both go away. And so when you type into your calculator, you just need to be super careful to make sure, I would almost make sure that whole exponent is in parentheses also, so the calculator doesn't get confused and think that this portion over here is outside of your exponent. And anywho, when we do that, we get 7 times 10 to the 5. I'm not sure why the book decided to round to 1 sig fig in this sample problem. So 6.60 times 10 to the 5. What's the unit for this equilibrium constant? And there is none because we never use units for equilibrium constants. So take a moment and ponder this question and see if you can find which of the following statements is true. Okay, and the correct answer is E. If Q is greater than 1, then our non-standard delta G must be greater than our standard delta G. If you're confused about this question, or if you'd like more practice on the problem that we just finished, you should try sample exercise 19.11. Almost done. Try this KSP problem, relating it to delta G naught. Do your math on your paper and give it a shot. And the correct answer is E, positive 265 kilojoules per mole. And you can refer to sample exercise 19.12 if you're not feeling so great about this one. Coupled reactions. Many, many, many chemical reactions are non-spontaneous. For example, let's look at this reaction. Let's say I want to extract some copper from copper 1 sulfate. This is a mineral called chalcolite, and I want to turn it into copper, but the problem is I can see my delta G for this reaction is positive, which of course means it's not going to occur. So how can I make this happen? I need some other way of doing work on this. I need some way of adding energy to get this to happen. And one clever way of doing this is finding another reaction which can kind of drive this reaction along. So I'm going to try to find a reaction that's spontaneous, and if you kind of think of it, kind of pull it up the hill. So how can we force this reaction to happen? By coupling it with another one which is spontaneous. Here's the catch. They have to have a common intermediate. What does that mean, common intermediate? Well, I'm going to need to see one of these things from this first reaction, either copper or sulfur, then used up in the next reaction. And obviously I don't want my copper to be used up, because if I'm mining this mineral, the whole point is to get the copper out and make it pure. So let's target this sulfur, which nobody really likes sulfur anyway. So let's find a spontaneous reaction that uses sulfur and turns it into something else. And here's a possibility. Sulfur reacts with oxygen to form sulfur dioxide. Now this is kind of a pollutant, but who cares? Just kidding. We see the delta G for this reaction is quite negative. So we've taken a non-spontaneous reaction that we want to occur, and we're making it occur by coupling it with a spontaneous reaction. So do you see that all of the sulfur that is produced in the first reaction is going to be used up in the second reaction? So I think you remember that if we go to add these reactions up, then anything that's on both sides cancels out. And so our overall reaction is going to be copper 1 sulfide plus oxygen turning into, copper plus sulfur dioxide. And since Gibbs free energy is a state function, we can also add up the delta G's for just those reactions. If you recall, if we needed to double a reaction, we can do that too. And anyway, we come up with a new delta G of negative 214.2 kilojoules. So by coupling these reactions together, we are taking advantage of this reaction and using it to kind of pull this other reaction along. Let's take a look at a very, very important example of coupled reactions, which the College Board wants you to know. A very important coupled reaction. Without coupling, many natural processes would not occur spontaneously. So for example, it requires energy to do many complex cellular processes that we depend on. Protein synthesis, transcription, translation, DNA, creating cellular organelles. And so one example that you might remember from biology, ATP, the energy that the cell uses to get stuff done. So on the one hand, we've got this nice thing. Inside of you right now, your cells are burning up your glucose. This is called metabolism. So your food gets broken down into simpler components like glucose. And then that glucose basically gets burned. It gets split apart. And we see those same old products of combustion over here, CO2 and H2O. Of course, we need oxygen for this to happen. That's why we breathe. And also, this reaction is exothermic, so it produces energy. The problem is, this glucose metabolism is not happening everywhere we need it in the body. It's not like this energy can immediately go from this molecule of glucose to something right next to it. This is happening in a different place. And so we need the energy currency of the cell. We need some ATP. So adenosine triphosphate. You know that ATP has high energy. And then once we spend that ATP, it turns back into ADP, diphosphate. It also makes some inorganic phosphorus waste, which your body gets rid of. So ATP is like the currency for the cell. You get rid of something you don't want, which gives you money, for example, and then that money can be used for other things that you do want to do, like turning simpler molecules and monomers into bigger things in the cell. So this is a coupled reaction. It's coupled because we can get this stuff, which is not spontaneous, to work when we couple it with a reaction that is spontaneous. And actually, it's this that is the spontaneous part that we're coupling it with. So by using ATP to do our non-spontaneous work, we've coupled it with a spontaneous reaction which can get stuff done. Another very similar example to this, and don't let this next slide overwhelm you, this comes straight from the College Board and what they want you to know. So external sources of energy can be used to drive change in cases where the Gibbs free energy is positive. So this first one we're going to learn about in the next chapter. So we can use electricity to make a non-spontaneous process spontaneous. So a good example of that is recharging a battery. So batteries discharge spontaneously on their own, but if we want to recharge them, we've got to get it kind of the ball to roll back up the hill, and that requires energy. But the reason I'm showing you this is specifically this part down here. So plants do basically the same thing that we just learned about, but in reverse. They're taking carbon dioxide and water and converting it into what? Oxygen and glucose. And the glucose is what the plants are using as their energy source. What catalyzes this? Well, obviously we need light. So light photons come in. There are photons that are in the range of visible light, actually. And this is why, for example, chlorophyll is green, because it absorbs photons that are in that range and reflects back the green light. But anywho, this delta G is very, very, very not spontaneous. So it's very strange for carbon dioxide and water to somehow turn into this complex circular ring molecule and oxygen gas. But with the photon, it gets enough energy to do that. So that's an example of a coupled reaction. So I'm going to leave this slide up so that you can look at exactly what the College Board wants you to know about coupled reactions. So hopefully by the end of this video, you're feeling pretty good about how to handle delta G when we're not under standard conditions, and you have a good idea of what a coupled reaction means.